In my last two lectures, I have introduced the concept of mathematical expectation, especially for a simple random variable. Now, we know that a random variable associates number with the outcomes of some random experiment. That is, whenever we talk about a random variable, we have an underlying random experiment. The goal of today's lecture and the subsequent lecture is to interpret the concept of expectation of a simple random variable in terms of something called the law of large numbers in probability and statistics. So, the law of large number is one of the fundamental results in probability and statistics, and there are several versions of it. The first law of large number, called the weak law of large number for Bernoulli random variables, was introduced by Jacob Bernoulli in 1713. So I will mention about that. Of course, it is a mathematical statement, and it will not make much sense if I just read that mathematical statement from a write-up. So I will talk about what it really means, and I will send you the notes of that statement and maybe discuss the proof as well. Once we have understood the first law of large numbers, that is Jacob Bernoulli's law of large number, then we will study more general versions of it, and naturally it will take more than one talk. But today I will just introduce why I think the concept of law of large number is useful, especially in understanding or interpreting the value of expectation or the mean of a random variable. So going back to our discussion on expectation, I have said that for a simple random variable, the expectation is the weighted average of its values, weights being the probabilities. Now, as I have mentioned, that with every random variable there is a random experiment associated. So for example, let us take the simplest example, the Bernoulli random variable that is associated with the coin tossing experiment. So if I toss a coin and x denotes the number of heads, so that is a Bernoulli random variable because it can take the value 1 and 0. Its expectation is p, but the random variable does not take the value p, it takes the value either 0 and 1. So I have asked what is the meaning of that expectation. So in this context, I will first mention Bernoulli's law of large number. So first of all, let us introduce some terms. So a Bernoulli trial is a random experiment which has two possible outcomes. For example, toss of a coin, head and tail. So we repeat a Bernoulli trial a large number of times, and there we count the number of let us say number of ones or number of heads in case of coin tossing. So with each Bernoulli trial there is a random variable which is associated. So a Bernoulli random variable is associated which assigns 1 and 0 to the two outcomes. So we repeat the Bernoulli trial n times and let x1, x2, xn denote the corresponding Bernoulli random variables. So it is 1 if there is a success or a head and 0 if it is a failure. Now if I add them up, if I add up x1 plus x2 plus xn, then I will get the total number of successes or heads, right? Now if I define x1, x2, xn, the sum of x1 plus x2, xn divided by n, that is take the mean, it will represent the proportion of successes, or in case of coin tossing experiment it will represent the proportion of heads. The Bernoulli law of large number tells us that if we repeat this Bernoulli trial a large number of times, then this proportion of heads or proportion of successes converges in probability to p, the chance of getting a success in one trial. Now convergence in probability is a technical term, and This is not expected to be known by students who are just taking a first course in probability statistics. So basically what it means is that if you give me any number epsilon, an accuracy level epsilon, and ask this question, that what is the probability that the proportion of successes, that is x1 plus x2 plus xn by n, will not differ from the p by more than epsilon, what is that probability? Now it is hard to compute. If I ask you to do the exact computation, then it is a difficult computation, but law of large number ensures that for large n, this probability is close to 1. That is a probability that x1 x2 xn will plus xn by n, proportion of successes, will not differ from the p by more than epsilon. That probability is close to 1. So what is the result? The result tells us that the interpretation of the p, which is the probability, and also the expectation of x, a Bernoulli random variable, is the following: that it represents the proportion of successes in large number of Bernoulli trials. Thank you.